Tonight's presentation is not only science meets music, it's actually the science of music. And I think we can all agree that most people, certainly all of you here tonight, find music captivating. And you know, you recognize that music plays an important role in our lives. It can affect your mood, it gets you excited, or make you calm and relaxed. But have you ever stopped to wonder why? What about those notes trigger the feelings or that memory? Why do certain chords make us feel melancholy and others invigorated, like you can't help yourself, you've got to be moving? Ultimately, to understand music, how we perceive it and how we produce it, requires that we understand how music is represented in our brains. And thanks to tonight's speaker, Dr. Daniela Sammler, we are beginning to understand the biology of music and why it is such a powerful force in our lives and how the musicians' brains are wired to produce it. So stay tuned for that. Now, our musical performance tonight is also from a neuroscientist who has an interest in the brain science of music and the therapeutic benefits of music. Dr. Patricia Izbicki earned her PhD in neuroscience from the University of Iowa and currently serves as medical science liaison in the therapeutic area of multiple sclerosis with the corporation called Octave. Her research interests include understanding the brain mechanisms of complementary therapies, such as music training, in aging adults and people with Parkinson's disease. And really important for this evening is that she's a classical pianist and harpsichordist, having earned her Bachelor of Music and Performance from the University of West Florida. Please join me in welcoming tonight's musician, scientist, Dr. Patricia Izbicki.
Hi, everyone. So before I start, David talked about how we're going to learn tonight about the music or the science of music. And so Daniela and I were like, hey, how about we design a musical program that fits that exact need? So the first piece or set of pieces by Alexander Borodin are really special because he was not only a brilliant composer, but he was also actually a brilliant chemist, and that was his quote unquote day job. So he's a phenomenal example of combining the arts and sciences in a beautiful way. And he's actually a co-discoverer of the Aldo reaction. So for those of you who are nerds out there, you probably know what that is. For those of you who are like, what is that? Crucial chemical reaction in terms of drug development and discovery. Also, one of the things that kind of touched my heart, he's a noble advocate of women's rights, and he actually was one of the founders of the School of Medicine in Russia. So I present to you Alexander Borodin.
It is my great pleasure to introduce tonight's speaker, Dr. Daniela Sammler, who is head of the Neurocognition of Music and Language Research Group at the Max Planck Institute for Empirical Aesthetics in Frankfurt, Germany. And may I just start off by saying, Daniela, thank you for coming. She had one of those plane flights from Germany that, you know, you'll never forget. I think she came out and they got all the way to Ireland, had to turn around, go back to Frankfurt, landing with fire engines all over the runway, and she still got on the plane and came here. So we really appreciate it. So Dr. Sammler is a world-renowned expert in the study of how music and language are represented in the human brain, using methods such as functional MRI, EEG, and transcranial magnetic stimulation. With her team, Dr. Sammler deconstructs and compares the sensory, cognitive, and expressive stages of music and language perception and production. Amazing work having people play the keyboard while they're in the functional MRI scanner. I mean, this is amazing. And basically, she is really generating a new, deeper understanding of the neural basis of music. She's the author of 2 books, over 60 scientific publications on this topic, and she's the recipient of the prestigious Otto Hahn Medal and Award of the Max Planck Society. And in addition to all of her exceptional research, Dr. Sammler has committed to science outreach and education. And she's delivered numerous public lectures and workshops on music and the brain, and has participated in a number of science communication initiatives to promote public engagement with science. Sound familiar? Okay. We're so pleased that she's come all the way from Frankfurt to be with us, and join me in welcoming Dr. Daniela Sammler.
Thank you, David, for this wonderful introduction. It's really a great pleasure and an honor to be part of this wonderful series which combines 2 of our passions, science and music. Ladies and gentlemen, tonight I would like to take you on a journey through the brain to understand how the brain plays music and what in turn playing music does to our brain. So, everywhere in the world, people make and enjoy music. In the streets, in the concert halls, and in the remotest places of the world. These musics couldn't be more different, but yet they all determine our social interactions. They enliven us, they move us, they touch us. And one very good example to illustrate that is one event that occurred in Toronto on a Tuesday night in 2019. Please take a look.
Why can't you see
any of you missed how much fun these people had singing together, and I believe some of you may have joined in, at least mentally, right? So this is a phenomenon that occurs not only in Canada, but also in the US, in Europe, in Australia, where thousands of people meet in concert halls to sing and enjoy themselves together. Actually, they are doing all the work themselves. They're paying for concerts where they sing. Now, where does this ability and this pleasure to sing and make music together come from? After all, what looks so easy is a pretty challenging task. So people synchronize their actions, they blend their voices, and they coordinate their parts, all without a lot of practice. Do we have anything like a musical sense, maybe? And why don't we see similar behaviors in other species? Or wait, do we? Certainly, there are a couple of species that do have musical abilities. For example, dolphins and songbirds, and also the elephants of the Thai Elephant Orchestra, who record quite a lot of percussion arrangements in their well-deserved retirement. The question becomes more interesting in species that are very close to humans. Let's take, for example, the bonobos. They have almost 100% the same genes as humans, but they don't gather in crowds and sing and dance. Or dogs. They have been man's best friend for at least 30,000 years. Plenty of time, you would think, to pick up one behavioral trait or two, but they don't. And it's not that they didn't have enough exposure. We know that humans have been doing music for at least 35,000 years. We know that because of discoveries of bone flutes, actually pretty close to Frankfurt in Germany, that were dated back 35,000 years. Music, however, is probably much older than that. We just cannot prove it because it does not form fossils. Darwin himself, he proposed that music developed in the course of evolution from courtship rituals and effective animal vocalizations. Essentially, he believed that musical males were just more popular with the ladies and could kind of transmit their musicality more successfully. But here comes a question. Is musicality actually heritable at all? And this is a question that was recently answered by colleagues in Nashville, Tennessee, and the MPI for Empirical Aesthetics. They asked over 500,000 people in the US one simple question. Can you clap in time with a musical beat? And what is amazing is that they could predict the answer to that question, yes or no, with significant Powerbluff chance from the genome of these people. So in essence, it was a collection of about 69 genes that were particularly relevant here. So it seems that our musicality seems to be grounded in our genome, at least partially. Now, another question comes up. How can our genes influence our behavior, like clapping to a beat? And here, the scientists also had a very interesting answer. Most of these 69 genes actually contained blueprints for our brain structure. So, next question. Why do we actually need a brain to clap to a musical beat? Now, the answer is because our brains actively construct the beat. And to illustrate that, I would like to invite you to a little experiment. An experiment that lets us experience that construction of a beat with you as the participants. Ready? Okay, what you will hear now is a series of tones. They will end at a certain point in time, halfway through the piece. Your task is to silently tap along with the beat. You can do that with your index finger on your palm, but please do it silently. And please also continue tapping when the beats stop, and try to keep the tempo as accurate as possible. To check whether who are good or not at that task? I will also play the last tone in this series. All clear? Ready to go. Well, even if that may not have been perfect now, in the lab, typically people land on the right time on this last beat. So this is just only one example that we are able to imagine and to hold a beat in our minds. But if we had, for example, measured in the lab your taps on the first 8 beats, we would have found that you were actually not tapping on the beats, but you were always a fraction of a millisecond too early. This shows that you were thinking along with the beats, that you were actually thinking ahead of the beats to plan your finger movements. So you were not reacting to the beats, but you were anticipating them. You were actively constructing the beats in your mind. Okay, let's do a last example, a so-called tick-tock phenomenon. You will hear again a series of beats. And now please tap along only on every first and third beat. Please pay attention to whether these beats or these sounds sound all the same to you. Ready? Here we go. Who of you heard the first and the third sound louder than the others? Okay, I see a couple of hands. Then you experienced exactly the tick-tock phenomenon. I can assure you that all the sounds had the same loudness. It was just your brain that constructed the second metrical level, actually by mentally emphasizing every second beat. So I think these are enough examples to show you how our brain constructs a beat. And so it's enough reason to think that what looks so effortless actually involves a lot of cognitive processes in the brain. And this is the reason why a whole field of research is interested in where these cognitive processes are actually controlled. To answer this question, researchers around the world, including us, use a method of functional magnetic resonance imaging. In these experiments, the participant lies with the head in the scanner while a brain activity is scanned, and they do experiments or tasks just as those as you did now. They hear the beats and the music via earplugs that we are just preparing in this picture. As you may expect, it's not just only one region that helps us or that guides us in synchronizing our movements with a sound. Here you see a right hemisphere of a brain. A piece of it has been cut out to also see the deep levels of the brain. And of course, it's first and foremost auditory regions and motor regions that enable us to synchronize movements to sounds. In humans, these areas, auditory motor areas, are interconnected via a thick, wide matter fiber bundle. Actually, it's like a data highway with a high transmission rate in both directions. We also have areas in the depth of the brain that are responsible for finding the beat and for constructing these different metrical levels. Now, interestingly, this connection between auditory and motor regions is particularly strong in humans, but less strong in non-human primates. That means the data transmission rate is slower in these animals, which is arguably a disadvantage for synchronizing with a beat and making music together. To be fair, in these species, the connection between visual and motor areas is particularly strong. Perhaps one reason why, for example, rhesus monkeys can very well synchronize their movements with light flashes. So now the next question is, what happens in this audiomotor system if we are not only synchronizing with beats and music we hear, but when we are synchronizing with other people, when we sing, like in our pub choir example at the beginning of the talk. Now, this is the new Everest neuroscientists try to climb, to study brain functions in individuals during real interaction. One theory proposes that during interaction, we actually co-represent the actions of our partners in our own audiomotor system. In other words, we use our own motor knowledge to actively mirror the behavior of the other, to anticipate the other's actions ahead of time, to be able to adapt accordingly. Now, would we be able to find evidence for such a co-representation in people? We tackled this question by testing pairs of pianists who were performing duets together in the MRI. Well, wait a minute. A piano in the MRI, how is this possible? Now, at the MPI for Human Cognitive and Brain Sciences, we had the great opportunity to collaborate with a brilliant sound engineer from McGill and a traditional piano manufacturer from Leipzig. You see both of them here in this picture. And they constructed a piano, you see it here, with 27 keys, small enough to fit into the scanner tube, but still equipped with all the hammer mechanics and the haptics of a real grand piano. Instead of strings, we use light to transmit the keystrokes of the pianist. The light feeds into a computer, and the computer sends back the sound to the pianist's earphones in the scanner. The pianist is lying on the scanner bed. You see him here with the piano on top. And there's a little mirror, maybe you can see it here. And via this mirror, the pianist can see both her hands and also the scores that we present at the other end of the scanner tube here on that little screen. Okay. In our experiment, the pianist inside of the scanner was asked to play melodies of Bach chorales with the right hand, as you can see here. The pianist was accompanied by another pianist who was sitting outside on a normal piano and who played the bass line with her left hand. The pianists could hear each other via headphones, and they had the task to synchronize their performance. One aspect to be mentioned, perhaps, is that each pianist only saw the scores they had to play, so the pianist inside only saw the melody. Now, our crucial manipulation in this experiment was whether the pianists, prior to coming to the experiment, had practiced only their own part. It means the pianist and the scanner had only practiced the right hand, the melody part, or whether they had practiced also the part of the partner. So whether the pianist and the scanner had the knowledge how to play the bass line, yes or no, even though the pianist never ever played the bass line in the experiment. The theory now states that the pianist in the scanner would be more likely to co-represent the left-hand action if he had previously practiced it. Indeed, our results lend some evidence for that. We find stronger motor activity when pianists had practiced the other's part. And crucially, it's not only activity that is related to the execution of the own part of the melody with the right hand, but it's also activity that may reflect a representation of the bass line of the left hand that was not played by our pianists. Moreover, these motor areas crosstalked more strongly with auditory regions, probably via this data highway I was just talking about. So overall, we interpret this stronger audiomotor activity during musical interaction as an evidence that our pianists actually co-represented the actions of the partner during joint music making. While we are now still digging deeper into the exact mechanisms and the benefits of such a co-representation, we are of course also curiously following the research of our colleagues who do cross-species research to find out whether they would see similar phenomena in monkeys and other species. Let's stay tuned. So, what have we learned so far? We have learned that our genome and evolutionary changes in brain structure and function allow us to make music together. Now, another interesting question that, as we find, is conversely, how music making may actually cause changes in the brains. To start into the second half of the talk, I would like to tune you in with a little interlude from Daniel Barenboim and Martha Agerich playing Mozart's sonata for 2 pianos in D major, the first couple of measures. You may guess why we picked a piece by Mozart. It is because all the idea that music may change the function of our brain started with the so-called Mozart effect at the beginning of the 1990s. The seminal study by Francis Rauscher actually showed that college students performed better in spatial reasoning tasks after having listened to 10 minutes of Mozart compared to 10 minutes of relaxation music or 10 minutes of silence. Now, while this effect was not really replicated later on, other effects, so-called close transfer effects of musical training, appear rather robust. For example, we know that musicians have more gray matter in primary auditory areas of the brain. If we zoom in, for example, into the primary auditory regions of non-musicians and pianists, you see that the shaded area here, particularly in the left hemisphere of the pianist, is much bigger than in the non-musician. You see a similar effect in cellists, but here with a right-sided asymmetry. Right? And one could link these asymmetries to the special challenges and demands of the musical instruments pianists and cellists play. Very similar benefit is also found in the motor networks. For example, pianists show stronger fiber tracts between the brain and the hand than non-musicians, as you can see in this graph here. And again, there's also a different specialization depending on the instrument. While pianists show a symmetric increase of these fiber tracts to both the right and the left hand, string players show a special benefit in the fiber tract that connects to the left hand. Actually, the hand that plays the fine nuances of the melody, not the bowing hand, not the right hand. So altogether, it seems that the brain adapts to the demands of musical training and the specific musical instruments. In the last minutes of my talk, I brought you a study in which we investigated the neural specialization of musicians in a radically different way. We asked whether playing and practicing the same instrument, but with different goals, would shape the brain differently. I have to say that a lot of music cognition research focuses on classical music and on classically trained musicians. And in this genre, the goal is to expressively interpret composed music. It's often side-read, and it's often with high precision. Other genres have different goals. Let's take, for example, jazz. In jazz, the focus is more on the creative manipulation and the improvised generation of ever new melodies and rhythms, the flexible invention of new things, and to adapt to to change course in the musical piece. This is seen, for example, in the scores of pianists. Here, it's not rare that classical pianists actually mark the finger patterns they will use during performance. So here you see a 2, 4, 5 they will use during performance. This is to fix a specific finger order and a very expressive finger order for performance. The lead sheets of of jazz pianists look fundamentally different. They tend to rather mark harmonies and harmonic relationships that can then be developed flexibly during the performance. And to illustrate that, I brought you an example of Michael Wolny, who we actually collaborated with in this experiment. Please take a look. So in our study, we asked whether the brain also adapts to the demands of different genres. More precisely, would we be able to trace differences between classical and jazz musicians, even if they play the same musical instrument, the piano, and even if they play the same musical piece, they just differ in their self-conception and in their general goals as musicians? We tackled this question using electroencephalography, or short EEG. This is a method with which you can record brain activity with millisecond precision from these 64 channels that are placed in this cap that she is wearing during performance. The crucial point is what the pianists had to do in our experiment. They were asked to play sequences of chords that we presented in form of hands on the screen. We did so to kind of rule out different preferences for different types of scores in our classical and jazz pianists. These sequences were all unrehearsed, but they were musically logical, except for the final chord. The final chord could be either completely regular or contains one of two different violations. So either it contained a harmony violation, so a chord with which you would never end such a sequence, or it contained an unusual fingering, like a very uncomfortable fingering that you can use, but you don't have to actually. The question is how our classical and jazz pianists would react to these two types of violations. Note that they were asked to play these violations as they were shown on screen. What I show you here is the brain potential of one electrode at the back of the head of a classical pianist. 0 is the point in time when the pianist sees the harmonic violation on the screen. For comparison, I also show you the potential evoked by the regular chord. And what you see is that around 600 milliseconds, these two curves diverge. I shaded it in gray. This shows us that a pianist detected the harmonic violation and reprogrammed their action plan, actually to play the harmonic violation instead of the regular chord they already had in their fingers. The same effect is found in jazz pianists, with one crucial difference. It starts about 200 milliseconds earlier. And these 200 milliseconds are decisive. They are decisive for pianists to play these harmonic violations without hesitation. Our classical pianists, they lost a couple of milliseconds imitating these violations. So we take this result as evidence for the higher flexibility of jazz musicians to react to unforeseen changes in the musical piece, as is needed in improvisation. In turn, our classical pianists were better at imitating the weird finger patterns. Actually, they did less mistakes in that than our jazz pianists, which we take as evidence that classical pianists focus much more precisely on finger patterns, as I've shown you in the scores. So altogether, we believe that the brain potentials and the behavior of our pianists reflect different priorities of different musical genres. The expressive interpretation in classical music versus the readiness to improvise in jazz. This brings us all back to the beginning of the talk. So the relationship between music and the brain is mutual. It's a constant give and take between our biology, the brain, and our musical behavior, between our genes and the challenges of our musical environment. Now, the question that is currently driving the field is how we can capitalize on this interplay. Can we use the power of music in shaping our brains to alleviate neurological disorders such as developmental dyslexia or Parkinson's? And would it help to tailor interventions to genetic and neural predispositions of our clients? Well, while we are waiting for these answers, we should simply follow our natural musicality and sing and make music together as much as we can. Because as you've seen in the very first example, just a few beats and chords bring people of all ages, of all skin colors, of all physical and mental abilities to harmonize. And this is, in my view, a very small investment to make the world a little better. Thank you very much.
So we have one surprise for you for the end. So Daniela so eloquently spoke about the Mozart effect, and Mozart needs no introduction, but we thought it would be a fun thing to include a well-known piece that you might not know is he actually wrote variations too, but it'll be played in the classical and then in the jazz, and I know you will know which one is which. So, so Mozart, and I am not going to say the title. I think you will know what it is.
And thank you all for being with us this evening, and look forward to seeing you again next year or even sooner, okay? Stay in touch, and thank you so much.